did actually his PhD here in Zurich, ETH, and went to Stanford. After that, came back to Zurich with an ambition. Got a starting grant, university starting grant that he took to University of Nice Observatory. Yeah.
Both actually, yeah.
And then he got a faculty position, University of Vienna, and he's like one of the well-known experts in cosmological simulations. I think he's
Well, the other ones are in the audience here.
but he's written like one of the definitive reviews about N-body simulations, I think, together with Bao, who studied the subject. Probably might have read some of his work, and he's going to talk about cosmological simulations, I guess. So the floor is yours.
Thank you so much, Julian, for the very nice introduction. Indeed, so it's very nice to be back in Zurich. It's been a while. It's great to be here and talk a bit about the stuff we've been up to in recent years. This mostly work with my group in Vienna, mostly pushed by Florian List, who's a postdoc with us. Now, most recently, Thomas Flöß, who's also a postdoc. Cornelius, who was for a long time a postdoc with us, now moved to Zagreb. And Lukas Winkler, PhD student of mine, who joined more recently, Natalia Porqueres, who's from France. Okay, so there is a DJ here and some structure formation, and I hope by the end of the talk you understand why there is a DJ and why there's structure formation. Otherwise, please do complain to me. Okay, so I was told there's a fairly general audience, so I tried to not lose everybody on slide number 1. So let's start with this slide. So effectively, what we'd like to do, I guess, in the next years, is sort of consolidate this picture of cosmic history, together with all the modeling, and see if there's any sort of mismatches and tensions. We had yesterday a very nice discussion over the DESI results already. For those of you who know, like they confirmed some tensions. So interesting times. Is the model going to survive? Is there going to be new physics that's showing up now that the modeling is getting active enough? But effectively, we have this picture where we start off with sort of an inflationary period in the early universe that has replaced the traditional Big Bang model, which gives rise to primordial perturbations, which grow in the early plasma phase to then leave sort of the first electromagnetic baby photo of the universe, which is the CMB. Thereafter, we have the sort of a dark ages phase where matter is mostly just sitting around and moving a little bit before we start entering the very nonlinear sort of more local universe, maybe up to redshift 10 or something like this, that we can start probing now, a little bit higher maybe. And so we have this cosmic web made up of galaxies. And of course, the information of the primordial perturbations plus the sort of gravitational, yes?
There's a problem with the slides. It's still on the first slide somehow on Zoom.
Okay.
You try. There are a couple of people on Zooms. We can.
Ah, it's paused. Why is it paused? How does you
know? Maybe
But how do you unpause it?
Maybe stop sharing and do it or resume.
Ah, here is a resume button. Okay. Doesn't do anything.
Doesn't do anything. Okay. Maybe stop sharing and share again. Maybe then it starts working.
Okay. So no, but okay. Zoom. Share screen.
Oh, yeah,
Keynote. Share. And now full screen.
Yep.
Why does it pause?
Maybe try to share
the whole desktop. I see, because it's probably opening a new window where it's putting it. So let's do indeed that.
Okay.
Yeah.
Can you try move to the next slide? Or...
Yeah.
Yeah, no, it works. Thanks.
Okay, so, okay, good. Where was I? Let's start again. No, okay, so we basically have, and you'll see later how many more modes in principle, sort of, so how much more primordial information in principle we can probe on these scales through the late universe if we can access it. And so I will sort of talk mostly about how we can model this era at the precision that we sort of hopefully had for the CMB. Exactly. So the key thing is, in the end, we have a lambda CDM or minimal extension of lambda CDM now, where we have our, all the parameters that you learned in your cosmology 101 class, plus your dark energy equation of states, or something that's also where we have the strongest constraints from large-scale structure still is on the sum of neutrino masses. What we hope to probe also is sort of, if this period of inflation really happened, then this should leave hopefully some signature in the primordial perturbations that should also be in principle be unravelable from the large scale structure. Okay, so we have a parameterized model. There is assumptions about you can in some sense you can exchange any sort of aspect of this minimal consensus extension of lambda CDM for your favorite model, but the model space right now is much larger, and so we hope with the upcoming era of large surveys to cut into this. Exactly, and so the modeling challenge in the end is, given a model, predict the observables and see whether we can constrain any parameters of the model or find tensions or discrepancies between the physical model and our understanding of the whole history of the universe. The observables that we have is actually a whole lot of observables that we have. Galaxy distribution itself, the shapes of galaxies. So at zeroth order galaxies are points, and next order galaxies are ellipses, and that's as far as galaxies are what I'm concerned with. Galaxy clusters, the hot gas sort of allows them to be observed also through the CMB and through the Zimmermann-Salzowicz effect, and then also in principle the intergalactic medium through the Lyman alpha forest or H1 intensity mapping can be used. Good. So of course there is a lot of data. So if this is our CMB map, that's a lot of pixels. But because our universe is, as we hope, should be statistically isotropic and homogeneous, you can compress this information since it's entirely Gaussian. So if to the assumption, well, there's modifications from inflation that sort of would predict that this is non-Gaussian, but they're very, very small. So if you assume that it's Gaussian, a Gaussian distribution is described by its mean and its variance. And so effectively you can compress this whole picture here, because if it's Gaussian, into this function, if it's isotropically Gaussian, because this whole statistics of the map should only depend on the separation between two pixels. And so the covariance between two pixels is compressed into the power spectrum, and all the CMB analysis therefore can sort of be done with this, so what's called summary statistics. And with Planck, or maybe even a bit earlier with WMAP, this has opened basically cosmology from being a bit storytelling maybe, to something which can make sub% accuracy measurements. For example, the baryon content joined with h squared, you see here 0.02 plus or minus 0.0002. So that's a 1% accurate measurement. And that's really a new thing sort of that happened for the first time with the CMB. Exactly. So in some sense, that's all there is to say about the CMB is this curve. When you see the lambda CDM model fits extremely well the data, especially on the high L. Here you have cosmic variance and also foreground contaminations, which sort of are a bit tricky. So that's why there's this discrepancy here. Good. We can also constrain from this sort of this detection of primordial non-Gaussianity, but it's consistent with zero. So it'd be great to have additional probes which are potentially more sensitive for this. Okay, if you go to the late universe, so then at late times, this is the nearby galaxy distribution from the 2-mass survey. Well, there's also one more galaxy that's sitting here, which is ours. And then all nearby galaxies, you see that this is no longer like a Poisson set of points, but they're actually correlated, and they're sort of correlated into these filamentary anisotropic patterns. So it's very clear that this cannot be described sort of by Gaussian statistics in the same way. And so the way you can extend this is you can say, well, if I have a Gaussian distribution, mean and variance is enough. But if so the 2 point, so if I now have a skewed distribution or one with kurtosis, I have to take into account higher order moments or cumulants of that distribution to account for that. And in principle, there's even a mathematical theorem. If it's non-Gaussian, then in principle, you have to take all of them into account. But the nice thing is, if you stay on large scales, then basically you expand this, you can expand this now into 2-point, 3-point, 4-point endpoint functions. But since you're correlating two pixels with densities effectively, and the densities is small, so if that's smaller than 1, these are suppressed as you go to higher and higher, right? So these will be sort of, you'll have a small 3-point contribution. 4-point will be very small as long as you're close to Gaussian. But if you go into the very non-Gaussian regime, then in principle, this might not be the right description. And so people have been discussing a lot of alternative statistics to compress the information, skew spectra, or sort of more machine learning motivated things like wavelet scattering transform, where you take all possible transformations, compressions of your data that are consistent with symmetries or KNN functions, or sort of more astrophysics motivated things like void size functions, where you just sort of try to find underdense regions in here and measure their sizes, or cluster mass functions. So all of these are some sense alternative statistics to compress the information of the full distribution of the galaxy distribution. And so in some sense, there is a big hope that, because the classical analysis is just doing this 2-point. So for example, I mean, most vanilla analysis that's been done by the big surveys is this famous 3 times 2-point. When you have galaxy positions and their ellipticities, you can correlate points and points, points and ellipses, and ellipses and ellipses, and that gives you 3 times 2-point. But the hope is by accessing beyond this 2-point information that you can sort of get much more accurate measurements of cosmological parameters. So this is, for example, a study for this wavelet scattering transform by Valogiannis and Dworkin from a few years ago, where you see these are sort of the contour ellipses for the forecast of the measurement of various cosmological parameters. It doesn't really matter which ones they are, with the standard power spectrum analysis, and then with a wavelet scattering transform. So unfortunately, I think a lot of people are arguing for these alternative statistics. It's sometimes a bit hard to compare them really apples to apples, because the systematics is very different and so on. But the hope is really that sort of you can, with the same data set, you can make a hugely improved sort of measurement if you choose better statistics. And the thing I will argue for, because I think it's cool and we can in principle do it, so we should do it, is that we just should be not, we could also try to not do any compression. So what does not do any compression mean? It means that we not only sort of reconstruct model some summary statistics, but that we try to model the actual observed universe. And in order to do that, we sort of have we have our model vector, which is theta, I call this, right, where you put all your cosmological parameters and whatnot. But you also have a vector which contains your specific realization of the universe, right? That's our universe, that form. And what we would like to do is infer that given all the data that we have. Okay. And the way you can do this, of course, actually, I think I learned this first from Robert, because he was working on Bayesian statistics in his PhD, is of course you can invert this with Bayes' theorem, where you have sort of the evidence, right, which drops out, so you get only a proportionality here. But all you need to do is write down a forward model, which, given your cosmological model parameters and your initial conditions, gives you a model of the data. And then you multiply with a prior, which in the nice case of this initial data, you can assume that's just sort of a white noise field, completely uncorrelated, and everything else is produced. Everything else is produced by the model. And you need to put in some prior on the cosmological parameters as well. And so how do you model then this likelihood? Well, in the end, that's just sort of a least squares aspect, sort of the idea you just take sort of a metric, a quadratic difference between your model prediction and your data, and you have some noise level, which in the end sort of, once you take, which in the end sort of weighs the importance of your data versus the importance of your prior knowledge. Exactly. So if you, in principle, we should be able to do this. And sort of that's what I will try to convince you that I think we might be able to do. So this aspects of this have been done by people in the past. For example, the Bohr collaboration, they worked a lot on being able to do this without reconstructing also cosmological parameters at the same time. So only the W, so that you can basically get the initial conditions of the local universe and get all these sort of local structures reproduced. Okay, so the picture basically is we input model parameters and a specific initial condition realization of our universe. Then we run some prediction for the matter evolution. Then we predict based on this the observables, and then we want to solve the inverse problem, going back using Bayesian inversion effectively. Okay, so what modeling aspects do we need to be able to do this? So we have to start basically going from the white noise, which you can think of, that's your some kind of abstract quantum fluctuations in the early universe, to through the early phase of the universe, where you have all the CMB physics going on, and then the linear phases of structure formation. And then we have to transition to a nonlinear model, which you can do either perturbatively. So a lot of this is pushed by what's called EFTs. I'm not going to spend much time on this, or using simulations. And so if you want to push to very, very small scales, effectively, I think it's only simulations that can do this really reliable. So if you want to go to the smallest possible scales, you have to do it effectively with simulations. Okay, so if you want to do this inversion, there's effectively two things. One I already showed is you write down explicitly your likelihood and you try to invert it. And the unfortunate thing is, you might think, well, that's crazy because that's at least million-dimensional parameters race, right? So say I want to reconstruct my initial conditions of the universe in a 100-cubed box or something like this, then that's 10 to the 6 dimensional space for that, plus, I don't know, 10 dimensions for your cosmological parameters. And so it turns out that, in fact, there are methods which really are efficient at sampling this, but they have to rely that you're able to take a gradient of your posterior with respect to both your cosmological parameters, but also with respect to your initial white noise, right? So effectively, you have to be able to say, if I change my white noise, how does my model prediction change in a sort of the Taylor series kind of way? And when you have this, then you can use what's called this Hamiltonian Monte Carlo. They guarantee, because they sort of rely on Hamiltonian dynamics in your parameter space, that your transition probability is always close to 1 because your Hamiltonian mechanics is reversible. And so you always have this detailed balance condition fulfilled. Or you don't write an explicit likelihood, and that's what's called simulation-based inference, implicit likelihood methods, where you just sort of train a neural network to do this job for you. And so in some sense, either you have to run 1 million of simulations, or maybe not 1 million, let's say 100,000 simulations, to cover your prior and train your neural network to get your implicit likelihood, or you have an explicit method where you in the end have to run your millions or 100,000 simulation in the evaluation of your posterior inside of an MCMC chain. That's sort of the choice that you have. I will talk about this. There are other people who can talk about this, so we also looked a little bit into this. But in whatever you do here, you need sort of simulations that are fundamentally different from the simulations that we've done so far, where you choose one model, you run, I don't know, you throw a lot of CPU hours at it, you have very high resolution. So we want something that's very fast. It should also be differentiable so that you can actually take these kind of gradients through it. And well, hopefully it should also be sort of written in a modern way. So we want to run many simulations that are accurate enough rather than huge ones that are super accurate in some sense, right? Okay, or maybe ultimately want to do a combination of the two, but that's sort of the focus I want to focus here. And so we built this framework over the last years called the Disco. Then now you know why the Disco, the DJ was there, which is called Disco DJ. So differentiable simulations for cosmology. That's the Disco. That's also the reason for this is all the software I developed, I think, since my postdoc years has something to do with music. So we have to stick with this. And the DJ is done with JAX. JAX is just one of these auto-differentiable frameworks which allow you to write code to which you can take gradients. So this is been developed by Google, which is mostly used for machine learning, where then you have to optimize for a loss function across your neural network, for example. So, and when you do that also with gradient based gradient descent methods and things like that. Okay, and so this framework should hopefully by the end of the year, we hope to make it publicly available. So it contains already Einstein-Boltzmann solver module, which allows you to do this early phase. I'll talk about this in a second. Contains sort of models for the large-scale structure, which I will talk about as well. And then it's something we're working on right now to also have it run efficiently on multiple GPUs. Okay, good. So this is a bit of a technical one, but bear with me. So one problem you might wonder is, okay, so I have the early CMB phase, and then we have our structure formation phase. And so I think only Julian is able to do most of the same physics across cosmic time, but we're not. So we basically have a different prescriptions at early and late times. At early times, we have sort of the Eulerian linear prescription, where the small things are all the fields, the perturbative quantities, but we have very complicated physics. In some sense, we have photons coupled to baryons, we have general relativistic effects, relativistic species, and so on and so on. Very complicated physics. But late times, everything is cold, everything is Newtonian, so it's much more simple physics. Well, we can have discussions about this. I think you only have small corrections to Newtonian gravity. I think we know that thanks to Julian, especially. And yeah, so it's sort of very different physics regimes. And so the way we're doing this at the moment is we have to piece it together. So we run sort of this Einstein-Boltzmann to the time when you're interested in your observables. Then you have a reduced linear model, which undoes all the physics that you can model in a linear way in your forward approach again. And then you go back effectively to A equals 0. And then either you use a nonlinear perturbation theory, which you put together with an n-body simulation to go then again forward with a nonlinear model, or you go all the way, and that's a new trick that sort of we came up with, that actually you don't need sort of a perturbation theory phase at all. Okay, so I have to talk about these two aspects of things. Exactly, so we wrote, well, this was my 2 summers ago or so. I unfortunately decided to waste my summer with doing this. So I rewrote basically a CAM or class in JAX. And if you're interested, you can access it from here. So this allows you to predict, for example, the transfer functions for baryons, CDM, neutrinos, and so on. And what you see is the relative error with respect to CAM and class. All with very high precision settings. And so you see across the board from 10 to the -5 to 10 to the 2, we're like well in the sub-percent. This is 1% error. So this is like 2 per mil error deviation. And you see that there is even some discrepancy between class and CAM at that level. Yeah, some difference at the neutrinos, but this is like in a heavily suppressed free streaming tail. So this is never relevant for structure formation. So what is cool about this? Because it's auto-differentiable. So these equations are stiff. So just for the numerical side of things, this is a huge set of sort of order 100 coupled ODEs. And they're stiff, meaning you have very short time scales coupled to very long time scales. And whenever you have a stiff system, you want to use implicit methods. I hope you learned that in your numerics course. And implicit methods are always painful because you have to take a Jacobian matrix of your ODE. And but if you have autodiff, you're done, right? Because it does it for you. So it's very easy to write implicit methods inside of these autodiff frameworks. So we spent some time doing this. Okay, now you have, I'm not going to talk about that. Let's look at the left side of this. So this is now the output of such a Einstein-Boltzmann solver across time. So x-axis is Fourier wave number. So left is large scales, right is very small scales, and the y-axis is time. So top is early times, redshift of 100,000, and here we are at redshift 0 today, A equals 1. And this is the gradient with respect to cosmological parameters of your matter power spectrum. And so I love this to now for teaching also, because it tells you basically if you change the cosmological parameter, how does the matter power spectrum change? And you just get it out of it's like one line of code, get this out. So for example, you can see all the things we know. So for example, if you change omega matter, you change sort of the amplitude of large versus small scales. You shift your baryon acoustic oscillation feature. That's this wavy stuff. You also see how the baryon acoustic oscillation travels from small to large co-moving scales up until you have recombination of the CMB when this decouples and it freezes in. What else do you see? You see W0, W8 is this dark energy equation of state parameters, which is sort of how the accelerated expansion of the universe is driven by something that's not a cosmological constant. You see how this sort of affects the small scales and the sound speed of your dark energy. That affects only super-horizon scales today, for example. So I found this very instructive to do this. Of course, you can also do it with finite differences with the classical class and CAM. And this is in fact how if you want to do a similar approach, you could do it. So you see that they all agree, except where there's some tiny differences. These are finite difference class, finite difference CAM, and this is the alternative that we have. So yeah, mostly agrees, except very close to zero or something like this. Exactly, but then you have at least 2 evaluations per dimension, right? So if you want to construct a whole Jacobian of many parameters, you have per dimension, you have to have 2 evaluations. So it actually becomes very costly to do this game. Okay. Another cool thing is now if you want to do forecasting with something like this, because so if you want to calculate a Fisher matrix, the Fisher matrix gives you if you have sort of uncertainties on individual variables, it gives you sort of joint constraints through your model. And that's effectively your known or model precision matrix of the observable sandwiched with 2 gradients of your model with respect to all the parameters that you want to predict. And so this you can, again, calculate with this alternative in one line. So you get a Fisher matrix analysis of your model extremely easily. And so this was a funny exercise because I've never done Fisher matrices before. So we repeated the Euclid forecast, so our result is this what is it? Light green one, and the official Euclid forecast is the purple one. So originally we looked at the original Euclid forecast and we got completely off. So I spent a week, but then luckily I was at some meeting and Julian Lesgourd was there and they found the same. And so he gave me their data from last year and actually we were very happy to agree. So there's only one thing where for some reason our constraints on NS seem to be different. So that's something somebody should sit down and hunt down. Probably a bug. Okay, good. So, yep.
Just one question before we move on. I'm a bit confused about this because you mentioned that for this kind of calculations, traditionally people do finite difference to compute the gradient.
Yep.
That's what I did and everything.
Yes.
But here now with auto-diff, what's the advantage actually?
That you just evaluate the gradient at your point location. So there's no finite difference. So you don't have to choose a scale on which you take your gradient. You don't have to choose, you do second order, fourth order, sixth order finite difference. You evaluate at the point both the function and the gradient of the function.
Yes, but don't they, I mean, these 2 methods should agree?
They do.
They do, right?
Yeah. They do, but with finite difference, you always have the problem that you have a bias versus variance trade-off because you have to choose a scale for the finite difference.
You mean the size? The
size, exactly. And then if it's not exactly symmetric at the point, then you get a, yeah, so this is sort of these errors that you see here are caused by this. Yeah. Exactly, and you only have to do 1 evaluation, so instead of, I don't know, 2 times whatever the number here is, 12, yeah. Okay, good. Then I move on to the nonlinear evolution. So if we want to model the later stages, then of course, sort of the universe looks like so. The contrast is very poor. So what you should be seeing here is some funky cosmic web forming with yellow dots, which are the galaxies, which you don't see. And here you see a simple 2D picture. Let me just repeat this. So what you should be seeing is that you start with something that's Gaussian. And then effectively, because you have gravity, which causes advection of your matter, so it moves around. basically you start concentrating matter where you have overdensities, and you start reducing the density where you have underdensities. And so effectively, you're in underdense region, you start zooming in on smaller scales, and on overdense scales, you start to push sort of the information from some scales to smaller scales. And so at 0th order, that's the effect that you want to capture, because on smaller scales, even smaller scales, you see, well, that's sort of probably inaccessible, because we have many, many modes that sort of accumulate in these very dense regions, and so they just all come together. So let me maybe give you more intuition for this picture. So in some sense, we want to describe now a patch of the early universe that somehow deforms under gravity into something. And so this is simply a mapping from one space to the other. And typically we will be using n-body simulations where we just put down points, and then we don't describe the exact sort of deformation that is happening here, but we just sample this deformation with discrete characteristics, because we have just you know, a family of these curves that go between the two spaces. And if we do this, then we can only do this in an approximate way, and I'll get to that in a moment as well. Okay, so how does this look like? So mathematically, this, if we only do Newtonian plus expansion, then this is governed by the Vlasov-Poisson equation. And so in the simplest case, if you have a single perturbation, a sine wave, so the velocity here is higher, here's positive, here's negative, so this hump here will move to the right, this will move to the left. This will do something like so. So because it's collisionless, at 0th order, it will just cross through itself and it form this spiral. And because there's no scattering, so there's no, if it were a Boltzmann equation, right, you would have a scattering term here on the right-hand side, which would cause things to approach your equilibrium Boltzmann distribution in phase play, which means it should become Gaussian distributed. But because you don't have this, sort of it retains sort of its full structure. And in principle, you could undo this by just running it backward in time, right? This is fully reversible. Okay, so how does it look like now if I give up on this velocity dimension and I just look at it in space-time? Then it looks like so. So basically, our initial perturbation lives on this boundary here, and it sets the slope of the line. That's all it does. Sets the direction of each of these characteristics, because that's the only scalar degree of freedom that you have if you have scalar degree of freedom initial conditions. And in 1D, there is not more than that anyway, okay? And then you can show rigorously that, in fact, if there is no intersections of lines that affects you locally, then you always move on a straight line. And that's called the Zeldovich solution.
So left-hand side is the phase space diagram. And then
left is phase space, and this is projected into time and space. So time you see as a movie. And so now we're projecting downwards in the movie, and we're putting the different slides left to right. Okay. Good. So it looks like so. And so this moment here, when they cross for the first time, is the moment when let's go back. Is the moment of shell crossing when for the first time, so it's vertical,
right. And
then afterwards you'll have multiple intersections. So if I take a line and draw it down, I'll have three different contributions, right. And that's exactly when I'm here. I have multiple lines over the single.
Okay. The lines are the trajectory.
Lines are the characteristics. Yes. Okay. And then because gravity does its thing, so you form kind of a bound state in which everything just starts to orbit. And yeah, and then you have a second shell crossing here when and a third one even, and so on. So this is very simple in 1 + 1D and 3 + 3D. You can also chaos and other forms of mixing. So very complicated. But the key thing to take away from this is there are two important scales. So the first one is sort of you have these things which are very simple dynamics, straight lines, just with a slope. Basically, so if you wanted to reconstruct your initial conditions, you can do this for all the stuff that's not mixed into this region, right? In an easy way. In here, you can do it, but only if you have the full 6D information or full phase space information. Can you recover all of the information about this surface here? Otherwise, this is not possible. So in 1 + 1D, if you have velocity plus position information, you can undo it. But in a real universe, we have a 3 + 3 dimensional, and we can only observe 2 angles and 1 redshift. So you're only observing a projection to a 3-dimensional observable space, so you can never undo this fully. There's just no way. Okay, but out here, it's simple enough that you can, because nothing has mixed, and so you only need to account for the deformation. Okay, so there's another thing is sort of that globally, there's a time when everything goes on straight lines, and then afterwards you have this sort of these sharp features, and these sharp features, that's called shell crossing or caustic formation or shock formation, and so on. So this is sort of a non-perturbative effect that also puts a limit on typically where you can go, where you can push with perturbative methods. And I think it's something we haven't figured out how to go beyond this. There have been attempts, but with perturbative theories cannot. So that's why people have resorted to what's called EFTs, effective field theories, where you say, well, but these are small scale, so I don't care. So I integrate them out. And then you get sort of correction terms that you take along, and you can approximately then model things, pushing in time beyond this by removing small scales. But with simulations, there is no problem. Everything's well behaved. Okay. And we already know this straight line solution since 1970s old, which good. So just very briefly, technical slide. How do you do this in perturbation theory? You just write down your trajectory of these lines, starting from some initial point, and then there is a displacement, and then you write this displacement as a Taylor series and in different orders, and you get equations that then you can piece this together. So you get basically spatially dependent Taylor coefficients, and this is a time expansion. And you can look at how these coefficients look like in space, and they look like so. So this is this part here. This is this part. Yeah, we can do 30 or something. So this was where we did. This was fun. So because people have done these two in the past, but that we know a recursion relation, so you can numerically actually do all of them if you choose to. And so something interesting happens for me. You see that qualitatively this is very different, these two, and then you have stuff that remains, and it's very similar. So if I look at this I put my perturbation theory glasses on the side and put my data science glasses on, I would say this looks like, well, it's very efficient to compress most of the field, but then there is parts which are very poorly compressed by this. So what's going on? So this is just a side note because I think it's so much fun. Yes?
So this 1FT, 2FT, and so on. So you use this FT model to move forward.
Yes.
Is that what,
yes.
So 6FT looks why is it so homogeneous? Are you going back to the initial condition?
So I'll show you what in a moment. So you only have a few points that survive compared to the others. So the amplitude of these coefficients here is much larger than for most of the field. And the reason for this is that sort of your rate of convergence depends on your type of collapse. And so if you're close to spherical collapse, LPT converges extremely poorly. And so what actually happens is, because this is not the time that you should be using as your expansion parameter, you have to absorb basically all the dynamics into this. And so you get these stupidly surviving points, which are the centers of voids and clusters. So I can show you this. So this is, we're now going to 30 LPT, just if you're interested in this. So this is the solution that if you have taken a cosmology class, you've computed this. This is, in fact, just a solution for a closed and an open universe. So you take the Friedmann equation for a closed universe, right? It gives you a collapsing universe. So that's a spherical overdensity that is collapsing. Or you go to negative curvature, in which case you can think of this going backward in time with positive curvature.
What's y-axis?
Y-axis, that's sort of a displacement, right, of a shell.
As a function of time.
As a function of time, exactly. And then you can show that your equations are symmetric, but you can either have positive and negative curvature, or you have a negative scale factor with positive curvature is the same, right? For Friedmann universes.
Your curvature is a spatial curvature.
Yes. Yeah. Exactly. So what's happening is that your overdense universe collapses, and then at some point collapses to a point. And in fact, you can show that this curve that describes this in the end, if you rewrite this as your displacement for spherical symmetric, it has non-analytic behavior at this point. It has a critical exponent 2/3. So it means you cannot expand this into a time-Taylor series in a trivial way. And so basically, this is the convergence limiting singularity that you have. Should have learned this first year mathematics at home. So you build your series, it can only ever converge inside of this region because that's your radius of convergence. And because negative curvature is the same expansion, you also see a divergence on the negative side, even though there is nothing happening there. It just sees that, right? Because you have your disk of convergence. Okay, so this is basically limitations of your perturbation theory, and that's why you see these points surviving. Because sort of you see when you go from 1D collapse, the critical exponent is 5/2. So you can take some derivatives and everything's still fine. While here you cannot even take one derivative and it already blows up. So meaning already the velocity field associated with this thing has singularities. So that's the ill fate of your perturbation theory. So how you can do better? Well, you do simulations where you don't care about these things. So now you have your true trajectory that does something like this. So LPT is what does LPT do? LPT, well, you only have one step. Basically, it asymptotically approximates the true trajectory in the early time limit, right? And then you have to go to very high times. And at some point, structure may happen, and you will no longer be able to match the yellow curve to the blue curve. In a simulation, we do something very different. Because, well, this is one form of integrator, but basically we move with the right tangent to some point, then we recalculate the interaction at that time, we change the velocity of everything, and then we move again, right? Mm-hmm. And then you keep repeating this. So now there's a problem that, oh, that slide is screwed up. There's a problem that standard integrators that have been used in cosmological simulations cannot reproduce these straight lines that we've seen in the picture. Why is that? Because I don't know, people somehow never really worried about this. But it turns out it's actually a subtle thing that has major consequences. So effectively, the time integrators that people have used in body simulation were geared to reproduce nicely the effects of the very nonlinear small scale universe where you have many orbits in halos and so on, but not so much the large scales. And so there's an interesting thing. Sorry, I screwed this slide up with the order. So you can write formally these integrators like so, it doesn't matter the details, but you can generalize them by putting two arbitrary functions when you change your velocity. So this is basically, you change your position by adding some velocity times some time step. Then you change your velocity by rescaling your current velocity and adding your acceleration. And then you move with a new velocity in position space. And so for standard integrators, this is one, and also there's a different time coordinate here that's typically used. And so something nice is you can show if you want to exactly reproduce these straight lines, there is a precise relation between these two factors that they have to fulfill some condition like so. Details don't matter. And if you do this, then with one time step, you move on these straight lines, which is what you should be doing, right? You should represent a straight line exactly. Otherwise, you're effectively moving along your straight line, but in velocity space, you always constantly move up and down around the straight line with the standard integrators. Exactly. And so, in fact, Feng et al. 2016 realized this already, but the paper, I find it from a sort of numerical analysis point, it's very lacking because they sort of describe it as an approximate method. They don't prove any properties of this. So if you want to see all proofs actually about the method, we collected them in here, and you can show it has all these very nice properties. And there's another nice properties which they also don't point out. If you leave for this degree of freedom, this you can prove is the only choice that in addition is symplectic, which is the property you would like to have for the late universe. Okay, I'm not going to bore you with this technical slide. Can you do even better? Yes, if you give up on this symplectic property, which is sort of preserving a Hamiltonian structure along with it, then you can even build second order Lagrangian perturbation theory in your integrator. And so piece by piece, basically you're piecing together two LPT expansions of your along as you step in time forward. And so this is nice now because you no longer have those sort of these convergence limiting singularities because you're constantly re-expanding, and you also have no singularities as long. So it's much nicer behaved, and it's a very nice numerical method. And so you can now see, so we call this, Cornelius called this bullfrog. this method. Sort of, this is the residual at the individual particle level between the perturbation theory and the simulation. And so you see with this fast PM method, well, you get some residual with 1 LPT, and actually you get a slight reduction compared to 2 LPT. The reason is that you're evaluating your interaction in the future, and that is already a high order contribution in the perturbation theory. So you're doing slightly better than 1 LPT. And with this one here, we're doing a 2 LPT, and you see the residual goes even further down compared to 2 LPT. Again, for this reason that you're evaluating interactions at the future time, while for the perturbation theory, you always have to pull them back to the expansion point, and therefore lose orders in your expansion.
Here's the difference between fast PM and your
and the n-body simulation. One time step, only one time step, right? Because for more time steps, it gets more complicated. So you can see for one time step, basically, this reproduces now 2.5 LPT, right? And then you can do many of them. Okay, so in principle, sorry. Yeah, exactly. So in principle, you see that you can show that it's roughly 2.5 LPT, and yeah, it converges to NLPT for many, many time steps. So now we have, which is cool, now we have a method which effectively, if we do few time steps, we have something like a Lagrangian perturbation theory. If we do many time steps, we have something in n-body simulation. And so if you want to do anything in between, you can do anything in between, which is fun. So this is the 2 LPT prediction for some late time universe. And this is doing one simple time step. So you see it looks very much the same. So things were just moved too far, shell crossed. So you only get sort of density contrast on very large scale still accurate. Now, if you do 5 steps, in fact, it works already with 1 step, you get sort of the cosmic web. Sorry, with 2 steps, you get sort of large parts of the cosmic web, right? And this is if you had used Gadget, or I assume PGD graph would also give you this with 10 steps. Yeah, it would give you this. So you also get sort of this cosmic, but you see the large scale distribution is completely off. And that's because the perturbation theory is not built in. And then with 1,000 steps, you nicely converge to something that's very close to where we do 10 steps. And the differences that you get is really mostly due to the very nonlinear things, because the dynamics inside of halos is very complicated. And so in order to get the density profiles right, sort of you have to use n-body simulations effectively. But if you don't care about that, this works extremely well. And so just again, another technical plot. What we should take away. So this is now, how does the power spectrum converge towards some reference solution? So this is 1% here, a 1% error. And so you see the standard simulations, standard n-body simulations, they converge like so, which is maybe not necessarily what you might want. So the convergence is sort of all scales converge at the same time to the true solution. So that means, yeah, it's kind of not very economic if you, while with the others, because the perturbation theory they're always correct on large scales, and you're only approximating the small scale dynamics, which is much nicer because now the more time steps you do, the more agreement you get on small scales. So you can decide basically how expensive you have to make them in order to get agreement up to a certain scale. Yeah. And then this compares also this with a fast PM.
Well, can
and so on.
Explain? So the dotted is one.
So this is one time step, the dotted one, and this gives you roughly something like what 2 LPT also would give you. Now, if you go with the bullfrog, the red one is the most interesting one. When you do 10 steps, then you're already here. So up to K of 0.2, 3, 4. Also, you're at, I forgot what this is, 2 per mil or something like this.
And that's with respect to simulated.
This is one with the same cutoff. But this is a bit unfortunate in this paper. Do I have the other? No, I don't have it. So it's a little bit more tricky with a cutoff, but the general picture remains that. So also, if you don't put a cutoff in, so we did put a cutoff in because we wanted to control sort of the scale of the initial perturbations that are included. So this is with a typical, I think, K of 0.2 cut that people would do for EFT analysis.
in the initial condition.
In the initial conditions, yeah.
And the comparison here is to the simulation.
Yes, yeah. Exactly. So basically what people do now with to fix the LPT, you can add now counter terms to correct for the missing power. But that adds new degrees of freedoms that you don't need if you do the simulation. Okay, yeah. This one?
So if I understand correctly, the point is that you use 10 steps in this bullfrog method.
Yep.
And you get a similar accuracy as 100 steps at large scale compared to the.
Well, even more, right? Because you see here the 100, we don't have 1,000 distance. So maybe 100 would be good enough. I don't know. Yeah.
But if you increase your times with your bullfrog steps from 10 to 1,000.
Yeah.
Also reconstruct the accuracy.
Yes. Yes. Yeah. But this really comes from, so this is something we also started thinking more about. Can one do something to get the small scales correct, more
Yes,
quickly?
so I have a question regarding this. So, okay, let's suppose you want to get the halos correct.
Yeah.
Would you still gain in terms of computing with respect to a normal integrator?
Well, it depends what you want. So I think,
For example, yeah, or say go to K of 10.
To
in
K of
our
10.
spectrum, yeah.
well, I think you would gain if you use this at early times, because with the so your time step constraints at early times with the standard integrators are bad, because you're basically moving over large distances while not much is happening. And so even the large simulations spend a significant amount of time just going through this linear phase. So there you gain, you don't gain at late times.
So with this, you kind of kill the race of going from 1 LPT to 2 LPT to 3 LPT initially.
Exactly.
Actually, you're doing it on
Exactly.
the line.
Exactly. Yeah. So I'm running out of time. Sorry. So I have to run a race with the head. Let's skip all this. So in principle, you can even push this now because it's a perturbation theory informed thing. You can start at redshift infinity with just doing what I showed before, just putting velocity perturbations. So you start with a perfectly homogeneous universe and just have particles have different velocities. And then so you can run basically a forward light cone simulation, which we did this because it was fun. I've never seen it. So you see then sort of this is your redshift, and this is time. So this is the forward light cone. Basically what a photon sphere would see running forward in time. So you have the CMB here. And so you see how many modes in some sense are in principle in the late time universe. So if we can access that, that would be fantastic. Okay, let me also skip all these things. Okay, no, let me not skip this. So now this is fun. So we have these fast simulations and they're built into also an auto-differentiable framework. So now we can, in some sense, piece everything together. Einstein-Boltzmann, 2 n-bodies, 2 predicting contrast, really poor. This is a sort of a picture of the cosmic web. And you can take a derivative of your density field with respect to omega matter, and you see how your stuff should move around if you change the omega matter, for example. So everything is in place. And so Thomas first, who made the slide, so with him, we're working now a lot on sort of building this up, getting an understanding for actually doing parameter inference with this full pipeline. So how do you do this? Well, you take some true initial conditions and you run forward an n-body simulation. You smooth it, you add some Gaussian noise, and you try to reconstruct both your initial conditions and the cosmological parameters that were used to run that simulation. That's as far as we are. And so it turns out this works. So this is still with a very conservative cut because it's kind of tricky to do some aspects. So this is all work in progress. It should have a big banner over it. So it's also very low res because we're working, but in principle, it actually worked quite nicely. So we do recover both initial conditions and cosmological parameters that were put in. And in fact, with an accuracy, when we put a cut like this, that's slightly better than if you had used combined power spectrum plus bispectrum and only and marginalized over the actual realization of the universe. And so if you increase now this to go to smaller and smaller scales, it actually you start to win, because that sort of starts to be not very well described anymore by P plus B, but also you're entering more difficult terrain. So that's very much work in progress. What else is nice? Yeah, so the nice thing is now also, because it's a probabilistic inversion model, you can draw samples that are consistent with your data. That gives you in the end your ellipses, right? So in the end, these are all consistent now samples that change cosmological parameters and initial conditions, and they're all consistent with the data. So you see large scales kind of stay, small scale things change. Yeah, and one tricky thing is also that the noise level a priori, we assume it's not known, and so it's fit together with the data. So that turns out to be actually challenging, that the model has to decide where to use prior versus where to use the likelihood. Exactly. This is another sort of example. It's very simple to put in masks because you're always working in sort of observable space. So if you throw away now all the data outside of this cube here, then there's no problem because you just drop them from your likelihood. And so all of the stuff that's outside becomes dominated by the prior. So that's basically random universes, but they have to connect continuously, obviously, in a self-consistent way with where you do have the data. And so all these things are no problem. So basically incorporating in homogeneous noise levels or having weird masks is not a problem. Okay, I'm done. I think I talked for long enough.
Thanks a lot for the very interesting talk. There's all different questions raised. If you might some more, please.
So similarly, in the true-point statistics, you usually say, okay, we gain more information as we go to small and one case, but at a certain point there is a limit because we need to introduce more extra parameters and so on. Is it going to be the same with this field level? At some point when we try to, because you want to reconstruct a very small scale, at some point we don't have any more cosmology information there.
Yeah, so this is why I think we can get away with these fast simulations, precisely because we probably have to make compromises on small scales anyway. And we have to model the small scale. So with, I don't know, baryonification plus bias models and so on that have to absorb all the astrophysics that in the end we don't want to have to contaminating cosmological information. So yes, I agree. But then naturally, hopefully it should not matter. I mean, hopefully we see the point that you add more parameters and you just don't get any more information, right? That etc. Hopefully we do not see that it starts to degrade or something like this.
But you see, there is some cosmological information that we don't have in the power spectrum and bias spectrum together. Because from your plot, it looked like it was very clear that it was not very clear that you are gaining a lot of information with the field level inference.
This one?
Yes.
Yeah, but this is a cut at 0.1, right? Where basically you expect the bispectrum to capture everything.
Okay.
Right. That's a very perturbative regime. So the hope is that, so some experiments we did point on that if you had full dense access to the density and you're not dominated by survey noise or something like this, you can probably push this to 0.5 at best before you're not able to reconstruct primordial modes anymore, before they become completely washed out.
Yeah, just to follow up on this, I think it's beautiful, really, really cool. To play the devil's advocate. I told you that already yesterday. So it's, you know, things are Gaussian until k of 0.1.
Yeah.
Okay. And things become messy at k of 0.3.
Yeah.
So, except if we can really, I'm not so sure that these small scales we cannot learn anything in principle. I agree with you that we cannot learn anything in practice right now. But so you're targeting this k from 0.1 to 0.3 here, or just?
So I hope we can go as high as 0.5. Because I mean it depends in the end also on your survey density and so on, whether you can even access these scales reliably. But that would be the absolute like theoretical maximum at redshift 0, because beyond that, effectively, you know, it's you don't have information. If you just have the density field, you don't have information enough to go back at the field level. But that doesn't mean that cosmological information is lost, right? I think that's exactly the discussion we had. You see, we can still learn something about Milky Ways, about dark matter and small-scale power spectrum from observing Milky Way satellites, right? But we cannot reconstruct the initial condition at the field level that caused the Milky Way distribution of satellites today. So that's a different thing.
Just to with galaxy clustering, this may work. With lensing, K of 0.5 is already probably affected by barriers, for example.
Yeah.
Right. So you'll have to include them somehow.
You'll have to, yes, exactly. So you have to put some additional modeling in that, yeah. But that everybody has to.
Yeah, of course. Yeah,
So-
I'm not.
Yeah.
Have you heard of this EMED study?
Yeah, it's very similar to what we're doing, exactly. So that's basically competition. Yeah.
Is there any differences between you and Kevin?
So I like to think that we were sort of numerically more robust. So there's a lot of stuff that we didn't talk about. So we have many more different time integrators built in. We have discreteness suppression techniques. I think we have sort of more control on how some aspects of the numerics are done, but otherwise it's also just a very similar technique, yes.
And have you also considered like, or did you think about using this for like a multiple solver or a multiple based solver?
You mean fast multiple method? This is a particle mesh. The reason is that if you write with this code for these autodiff frameworks, it doesn't lend itself well to adaptive algorithms. So you're much better off with brute forcing certain things. And for this regime we're interested in, I think it's close to optimal, and I don't see a way. So we've been thinking about this, and it would be nice to do, but you always have the problem that it end up with an adaptive algorithm where you don't, for example, know the number of neighbors that you have to consider and something. So you have to make approximations, and that'd be fantastic to put in for as a small scale model. But it's right now we're doing experiments at this scale, so maybe 1 or 2 years would be interesting to look into this. For now, I think it's good enough.
But you already did consider, or you already have multi-GPU for
That's what we're working on this right now, because that's more what you would like to do is you see that some of these constraints get better if you have very big boxes. So if you 0.1 and then you would like to go to 4 gigaparsecs.
Do you have any, or yes, is there any like specific plan, or do you expect to run into like GPU memory issues when you do the?
So we are already, so we can do with this right now 512 cube simulation with a 1024 cube PMO. It's on one A100, 40 gigabyte. What we have, we don't have the 80s, and it takes 0.25 seconds per time step. So basically with these 5 steps, depending on what scales you're interested in, you can run 1 simulation per second, and that's how in some sense you can do these chains. Now, if you do the gradients through it, it's slower and it needs more memory. So yeah, that's why we haven't pushed it yet. But the biggest inference we've run is 256 cube.
So for galaxy clustering, you don't have like one of these 2D maps, right, of galaxy.
Mhm.
You have these 3D catalogs.
Yeah.
Are there technical difficulties in moving from one to the other?
You mean
Or
to
the-
redshift space and angles?
Yes, or the plan is you can just project your catalog into a 3D map.
No, so that's also something we're working on. In fact, Alejandro, who we talked with yesterday, that's sort of his first project to put in one of his first PhD projects to put in a light cone output directly. And because we're using many large time steps, right, you have to sort of do this inside of but there's no complication. Yeah. Sorry? Yeah. This one? This one? Mhm.
In the cosmology sense, I think the bound structure remain on the halos.
Yes, not only they're all collapsed structures. So in principle, if you have smooth initial conditions, you can form halos, you can form filamentary structures, and you can form these sheet-like planar objects. Yeah.
What about the particles that escapes?
Escape. Well, they should not escape. I think it's very hard to do if it's really a collisionless medium. There should be no halos, no particles that escape. So in some sense, once your halo forms, it's enveloped in material that falls in, goes to the other side, because that's sort of the highest energy material that's falling in. it will have the highest kinetic energy because you're at the highest current mass, right? So, and then it falls back in. And so this is this point of turning around after you fall in the first time. You go to the other side and you oscillate back around. That defines sort of the outer boundary of your halo. So if you choose some standard halo definition, like M200 or something like this, then often this cuts into this sphere, and you're sort of inside of this outer region of backsplash material. It's often called. Yeah, but there should, in some sense, there shouldn't be any particles that really go out, right? Because it's collisionless. If you have collisions, in some sense, you could have three-body interaction, which kicks something out. But if it's truly collisionless, I don't think this should happen.
So the baryons will break it.
The baryons will break it if you have outflows or something like this. Yeah. But you have to put in a lot of energy in some sense, right? I mean, I know we see this. Yeah, but even there, right? So that's AGN has all the gravitational energy of the stuff, you know. So yes, I mean, of course, that's what they do. They generate these big bubbles, but yeah, but it's only 20% of the mass.
No further questions? Yeah, thanks again.